at 40,000, it looks actually pretty good. And so again, things like, and that's what I kind of wanted you to think about in the long term, which of these, so again, log n, we can't even see it. It's so far to the bottom, and like n log n, again, is another curve that it eventually surpasses the 40,000, but it's nowhere near the n squared of the 2 to the n. I can change the color of this as well. Does this kind of make sense? So it's kind of thinking about which of these curves fall underneath the n squared curve. And if so, then they're all big O of n squared. That's what we're going to do. So this was just kind of thinking, okay, if I had to think about these curves, which ones would, I guess, would have a less steep curve than n squared. But in the exercises today, we're going to actually show over how we go through this process to prove it. So 2 to the n is going to be less than n squared. This is just n squared times a constant, so that is. These two are not, because obviously n to the 4 and n to the 3 will eventually, again, have more steep curves. These 4 are all fine, and then we just saw that 2 to the n is not. So again, we're really just looking at this n term. And again, anything with a larger thing is going to go up much faster. So again, n to the 4 and 2 to the n go up much faster than 2 to the n. If I change this to n to the 3, we'd see again it's still above that red n squared curve. Any other questions? So yeah, I know this was a tough quiz because again, we haven't actually gone over the big O exercises yet. So today what I wanted to do was jump into showing how we're going to show that something is big O of something else. Working through, I'm hoping we can get through all 10 of these exercises. So if there are no questions, we can jump right into these. And thanks, Finn. Because we can multiply it by a constant, by some constant c, and it'll always be above that. Which we'll show right here. Like right now, our first question will be something similar. Yeah, I mean, you could all, like, if I said, which of these are bigger than like 10 to the n, then they'd all be smaller. Again, big O is just things that are beyond it. So that's why some of these running times are really good, like a log n running time. It's always obviously going to be less than n squared. Yeah, exactly. Big O is just saying that it's definitely less than or equal to this, but it can be a lot. It can be much less than it. It doesn't have to be. It doesn't have to only be equal to it. Typically, what we want to provide a big O that's as tight as possible, though. We want, yeah, you could for lots of constants. We want to get kind of as tight as possible, just so we can kind of see where these key points are, if that makes sense. So in our graph, we have to zoom in to see where these key points are. But again, if we wanted to compare some of these, we'd say, okay, here's a key point for these two, and here's a key point for these two. And you'd kind of, so as long as my input size is bigger than, I guess, whatever, 6, I know that this red curve is going to be better. And as long as it's bigger than 10, I know that the purple one's going to be better. So there's kind of some trade-offs that you can make based on your input size. But in general, if we're thinking about having our algorithm in terms of scalability, we want it to be able to work with large input sizes and increasingly large input sizes. So that's why over time, our asymptotic analysis allows us to see which are the best choices as our kind of input sizes approaches infinity. So as it continues to grow. Does that make sense, Sabrina? Cool. So we can jump into this first one, and I think this might also answer when we work through this. It might also answer James's question as well, hopefully. So let me get out my pen. I'm going to move my tablet on top again. Try to use that today. Okay. So let's see for this first one, we've got f at n equals. My tablet just turned off, sorry. Okay, it's back. I think I bumped the power. So for this first one, we've got 10,000 n squared plus 25n. So what we want to do is, again, find some constants c and n naught such that the curve of this function, whatever it happens to be, again, the curve of this function, again, it can be whatever, some curve. We want to find a point that it's always, so we've got another thing. We want to say from here on, it's always going to be underneath this blue curve. That's what we're looking for. So we're going to say, okay, what is this n value for which this is always going to have a better running time than this other curve is really what we're trying to show here. So what we can do here is, so we'll start with 10,000 n squared plus 25. And we can say that is actually less than or equal to 10,000 n squared plus 25 n squared because we know that, again, all I've changed here is this n term here. Because we know that n squared is going to be greater than or equal to n as long as n is greater than or equal to 1, right? Because they're equal at 1, at 2, this goes to 4, this goes to 2, at 3, this goes to 9, and this is still 3. So we know that n squared is going to be greater than or equal to n. So I can easily rewrite this as saying that if I've got 10,000 n squared plus 25n, that's going to be less than or equal to 10,000 n squared plus 25n squared, as long as n is greater than or equal to 1. So by collecting these terms, we know that it's this 10,000 n squared plus 25n is always going to be greater than 10,025 n squared. So now we've found a c, which would be 10,025. So really this is all we have for this proof. So kind of right now, with all we've got right here, we can say that therefore f at n, sorry. And I'll try and show this in the plot as well in a second. So we can just say f at n is order n squared with c equal to 10,025 and n naught equal to 1. Because what we're saying is we've got this, it's order n squared, as long as we just multiply n squared by a constant, and it's going to be below that curve for all input sizes n and beyond. And I think so. Sabrina said we could have lots of answers. So let's actually think about a slightly different answer. So again, if we start with 10,000 n squared plus 25n, we could also say that's less than or equal to, oh, one too many O's, 10,001 n squared. But in this case, it's not going to be less than 10,001 n squared when n is equal to 1. Our n term is going to be, our n naught's going to be different here. Because when n is 1, this is going to be 10,001, and this is going to be 10,025, which, so it's not less than or equal to it. So we need to figure out for when, what is the n naught if we're saying our c is 10,001, which we can do. We can subtract 10,000 from both sides. And then we have that this is just n squared, and this is just 25n. If we divide n by both sides, we then have 25 is n. So in this case, we could say, so therefore we could say f at n is again still O of n squared, but this case with c equal to 1, and n naught is 25. So again, it's always going to be under this other curve, 10,001 n squared, for all input sizes beyond 25. But again, both of these are order n squared. Any questions about this? What I'll do if there aren't is I'll jump to the other graph to kind of show this. I'm happy with either one here. Both of them are just showing that we know that it's n squared because we've found a constant to multiply n squared with, and an input size that beyond, from that input size and beyond, it's going to fit under that n squared curve. So both of them are perfectly fine. What I'll probably require you to do in assignments and maybe future quizzes and stuff like that is just make sure that you provide the c and the n naught that actually works. So you know that if you multiply n squared by 10,025, from this point and beyond, it's going to be underneath that curve. Any other questions? If not, I'll jump over to the graph, this one over here. But I might have to erase the writing when I do that. What is n squared in the second one? What do you mean by what is n squared? I said the whole thing was O of n squared. I subtracted, so we've got this expression here, 10,000 n squared plus 25n is less than or equal to 10,001 n squared. But I wanted to see for what n this was true. So I subtracted 10,000 n squared from both sides. So if you subtract 10,000 n squared from the left, it gets rid of this term. If you subtract 10,000 n squared from this, it leaves us with just 1 n squared. Yeah. Any other questions? Okay, so what I'll do is I think I have to clear this for a second. And I'll go over here. And again, so our original expression was 10,000 n squared plus 25n. I have to scale my y up a bit more. Okay, So we've got this curve. Maybe I can take it down a little bit. One sec, sorry about this. How can we get this so it is actually visible? Start at 0. Yeah. So what we've got here is, if I add another expression, we first said 10,025 n squared. And again, it's really hard to see where these are different. Let me. As we can see, these curves are almost always the same. And I can add another one, y equals 10,001 n squared. And again, if I hide any of these curves, we see that there, but I guess if we really zoomed in, we'd see that the 10,001 n squared crosses with the purple one at 25. We see that there's a cross point right here. I'm not sure how to, I just found this tool. I don't know how to actually, I think if I set it to 0, it just shows the picture there, but it doesn't, I can still zoom out and it'll go past it. But I guess what I want to show is that all these curves are the same. I guess the point where these two cross would be at this 25, which is why there's a little dot there. The curves are so similar that we can't actually see that, but that is, I guess, up to this point, the red is below, which we can, they're almost the same. I guess up to this point, if we zoomed in really far, we see the red is slightly below. And then after this point, the red is going to be slightly above. Which I guess for this example, it's not great because they're such big numbers that we have to zoom in so far to see them. But as we can see, these curves are almost the same, but oh no, yeah, I erased it. But what our proof showed is that, again, we know that before that n naught, the other curve will be smaller, but after that point, it'll always fall underneath that other curve. So let's do a slightly similar one here, where we want to find out what is the big O of 4n plus 20n to the 4 plus 117. Because x, we're trying to figure out what x is. In this case, it was n squared. So for this next one, again, what we'll see is we can write 4n. Oops, I need to get my drawing tool. I'll answer your question in a second, Shanna. I'm not going to rewrite that whole question. So we've got 4n plus 20n cubed plus 117, and we're trying to figure out what the big O of this is. So again, we want to find some constants and an n naught such that we can find a function that's always greater than or equal to this. So again, doing what we did for for question one thing we can do here is just say, okay, I know that if I make these all the same n terms, so n to the cubed, I know that the term on the left is going to be less than or equal to the term on the right for all n greater than or equal to 1. Because when n is 0, this term here would go to 0, and the term on the left would be higher. So it can't be for n equals 0, but for n and beyond, for n is 1 equal and beyond, n to the 4 is always going to be greater than n and just n, and obviously no n term. So again, if we add up all these terms, we've got 141. So we know that 4n plus 20n4 plus 117 is always going to be less than or equal to 141n cubed for all n greater than or equal to 1. So therefore, we say that this f at n, sorry, I keep, is order n to the 4 with c equal to 141 and n not equal to 1. So again, we're just saying that this, what we're doing here is we're saying that this function will be less than or equal to the end of the 4 curve as long as we multiply it by this constant for all n greater than or equal to 1. No, this is how I've always seen Big O proved, and this is how the textbooks do it as well. You're again trying to find an upper bound for this, and you're saying that it's always going to be, it's going to fit in this end of the 4 curve. Any other questions? Not necessarily. I think today we'll at least see one exercise where it's not. And again, in our second example for question 1, we saw that our n naught, I think up here we have that for our second example, when c was equal to 10,001, n naught was equal to 25. So it depends how you set up your expression here. So what do we think for the third one? What is the big O of f at n 10,083? So we know it's going to be less than n and n squared and n cubed and n to the 4. Yeah, so Bryce is saying it's just a constant. And again, so here we can write 10,083 is less than or equal to 10,083, I guess, times 1. And this looks really weird because, I don't know, I guess usually whenever we see a constant without an n term, a proof isn't really required because it is just constant time. Again, we see that n, that the input size n has no effect on the runtime. So it's going to run, this is great, it's going to run, no matter how big our input size is, it's going to run the same speed. Yeah, so typically, Scott will want to find the smallest bound possible. Otherwise, we could say everything is big O of n to the n or something like that. Yeah. So yeah, I haven't really ever seen that kind of a full-fledged proof for a constant like this, but I guess yeah, for all n, I guess even input size 0 or beyond. So I guess therefore we can say that this function is just order 1. So it's constant time. It's yeah, 1 is constant time. It doesn't depend on the input size at all. I guess technically we could say with C equal to 10,083 and not equal to 0. Any questions about this? Okay. I'd like to move a little bit faster. I think these other ones are going to be kind of similar to question 3, where it's a little bit quicker to prove. So I'll clear these off and scroll down. So for this next one, we've got 3 log n. Oh. We've got 3 log n. And that's going to be less than or equal to 4 log n. I guess for all n greater than or equal to 1. So so again, for this one really quickly, we can just say that f at n is, or I guess I should say it's, formally I should do it like this, is order O of log n with and I guess the question 5 is just a small, I guess, extension to question 4. Whereas again, if we've got 3 log n plus log of log n, what we might realize is that log n is greater than or equal to log of log n for all n greater than or equal to 1. So again, I can say that this is going to be less than or equal to 3 log n plus log n. So I can do the same thing here and say that this is all going to be less than or equal to 4 log n. So again, we can just say that f at n is order log n. With c equal to 4 and n not equal to 1. Any questions about this? I guess why I gave us a lot of problems as opposed to maybe longer, more difficult problems is today I really just wanted to get us thinking about the process of just finding kind of a general expression that is greater than or equal to the term we start with, and then again, and then writing it out in this form that's saying it's big O of something, and given these 2 constants c and n naught. That's what you're expected to. That's what you'll be expected to do on the assignment, and again on the midterm as well. I'm not sure how I'll do this on the midterm because some of this is kind of hard to write out. But on previous exams, they've said something like all these functions are like, again, O of n to the x. Find the smallest integer x such that the function is big O of n to that x, and provide constants c and n naught to illustrate this. So that's kind of how these types of questions have how I've seen these questions on exams to test big O. So again, we're trying to find the lowest n. So we can't just say it's always n to the n. We need to n to the n. We need to say, okay, no, this is actually just n to the n squared or n to the 4 or whatever it happens to be. Any questions about this? Okay, we can move on to the next one. The last two, I think, will take a little bit more time, so I'd like to move on. Okay, I'll move my chat to that side. So now we've got, so 2 to the 17 is really, really, really large. What do we think this one's going to be? Yeah, so again, this has, the input size has no effect on this. So again, we can just say that 2 to the 17 is less than or equal to 2 to the 17 times 1. And so again, therefore, this is, I always do it like that. And our C is that 2 to the 17. So no matter what our input size is, we're going to say it's constant time because it's always going to stay at 2 to the 17. So for the next one, the next one is actually gets us to test some of our log rules. Does anyone know how we can rewrite 2 to the power of log 2 to the n? And again, we're assuming in this course we're assuming base 2. Yeah, so we can rewrite this as just, if we've got something to the log something of x, so it can be, if we've got x to the log x of y, we can rewrite this as y, right? So what I can rewrite this as is just 2n, which again, obviously is less than or equal to 2 times n. So we've got our C and our n naught right away. Oh, sorry. Is it still making sense to people? So doing these big O proofs for some of the exercises we've done so far, I'm not seeing as much stuff in the chat as usual. So I'm going to do a quick poll just to see how well this is making sense to everyone. Okay, so looking at the results here, I hope, can you all see the results? Yeah. Yeah, I think so too. So it looks like about half of you are confident. Some of you are saying, yeah, it makes sense, the stuff that you're doing, but that doesn't mean I can do it on my own. And some of you are starting to get there, and some of you, that's fine. there still are a bunch of you that doesn't quite make sense yet. So we'll work through some more problems. Yeah, fair enough. Okay, so we have 11 minutes to do these last three, which I think we can do, hopefully. If I can get my screen to not go over that question number. So I guess for this next one, how do we think the input size affects the running time if something's one to the n? Yeah, so this is kind of, I guess, another trick-ish question, because 1 to the n is just 1 for all n greater than or equal to 0. Yeah, the input size 1 to the power of anything is still going to be 1. But now we've got a little bit of a more difficult one. So now in this next one, we've got 64 n to the 1/2 minus 256 log n plus n log n plus 128n. So the first thing we're going to do is try to figure out what this is less than or equal to. But the weird thing here is we've got this one term that's minus a term. So what do we think we're going to do here? Any ideas on what we can do with this negative term? Yeah, we can kind of just say, let's say that's just for as long as n is positive, we can kind of just get rid of it, because just changing it to 0 is going to, if we're subtracting a large number, subtracting nothing is going to result in a larger value over here, right? This is going to be a larger value if we subtract 0 as opposed to subtracting something bigger. That'll decrease our number more. So I just wanted to show you something with a negative value, just to kind of show that it's actually, it's confusing when you first see it, but then if you think about it, if you just want to try to get an expression that's greater than or equal to this, we can actually just disregard that term. And then the rest is going to be, then we need to think about, okay, how do these n terms compare? How does n to the 1/2 compare to n log n compared to, I guess, no n? Oh, sorry. Wait, is there 128 n? Oh, sorry, there should be n there. So how do these n terms compare to one another? That was just a mistake. Sorry, David. Good catch. So I think the most dominant term here, if we think about it, we're comparing n to the 1/2 with n times log n with just n. So we're going to have as long as n is greater than 2, we're going to have it in this form. Because that's when this equates to, when n is 1, this term, if n was just 1, this expression, this part of the expression would no longer be true. So again, the most dominant kind of term here is n log n, as long as n is greater than or equal to 2. So what we can do is we can say this is going to be less than or equal to 64 n log n plus n log n plus 128 n log n when n is greater than or equal to 2. So the thing we had to kind of, this problem was a little bit more difficult because we had to do a couple of things. We had to, first of all, we got rid of the negative term. Second, we then had to think about which is the dominant term as our n grows, and it's going to be the n log n term. So really, if we combine these terms now, we've got 188, 92, 193 n log n. So this one was a little bit more difficult. This was one that, again, this is something more similar to what you're going to see in the assignment when you'll have a lot more time to think about it. But again, the steps we kind of did here was that we kind of got rid of the negative term. And then we looked at the other terms and decided which the dominant term was as n continues to grow. And we saw that, okay, the n log n curve is going to be above root n and n. So when we're comparing kind of lines, these two lines here, we saw that, okay, if n log n is dominant, we know that 64 n log n is always going to be greater than 64 root n, and 128 n log n is always going to be greater than 128, and as long as for numbers 2 and beyond.